Hey everyone, it's AI with Chucky and welcome back to the channel. Recently I made a video on how you can generate images with Z-Image Turbo on Google Colab using any custom LoRA for free. But many of you have already been asking how they can train their own LoRA, so I decided to make this video, and one of the bottlenecks for creating a LoRA has always been the several training hours this consumes, which made it very difficult for many people. So I decided to use the image to LoRA model architecture created by DiffSynth Studio, which on the free T4 GPU we can train our LoRA in just 10 minutes, which is absolutely insane, and you don't even need hundreds of images, just 1 to 6 or 10 images are enough, and this LoRA training doesn't need any trigger words or labeling. It focuses on what is consistent across our training images to create our LoRA. This can be the background, lighting, character traits, attire style, or traits. So when providing your images, you'll keep note of what you want, so you can make it consistent across your image datasets. If you have ever tried to train a custom style, a specific character, or a unique concept using traditional Dreambooth or standard LoRA training methods, you already know it can be a massive headache. Usually, you need dozens of perfectly cropped, high-resolution images, incredibly precise text captions for every single image in your dataset, and hours of tweaking learning rates, epochs, and optimizer settings. And even after going through all of that tedious manual labor, your final model might still turn out overbaked, inflexible, or completely unusable. But what if I told you that you could completely bypass all of that traditional training architecture? What if you could extract the exact stylistic DNA of an aesthetic using just 1 to 6 images with zero text captioning required entirely for free? That is exactly what we are going to do today using the revolutionary Z-Image architecture, which is powered by DiffSynth Studio. Now, before we get started, I need to address our choice of platform for today's tutorial. Normally, all our tutorials are based on Google Colab because it is incredibly accessible and familiar to most of you. However, because the Colab free tier only provides us with just about 12 gigabytes of system RAM, it simply won't be enough for our Z-Image Turbo LoRA training process. The extraction pipeline requires loading some massive models into memory simultaneously, which will instantly crash a standard Colab instance. So, instead of Colab, we will have to use Kaggle. Kaggle is fantastic because it provides us with the exact same dual T4 GPU setup as Colab. But the crucial difference is that the system RAM on Kaggle is 30 gigabytes. That is more than enough for us to do everything we need today completely for free. I will admit Google Colab is a bit more user-friendly compared to Kaggle, which looks a lot more geeky and intimidating at first glance. But I promise you, it still gets the exact same job done beautifully. To make this entire process as smooth as possible, I have actually written and created 2 different Kaggle notebooks for you guys today. The first one is a beautiful one-click web UI version that I made specifically to offer more convenience to my Patreon subscribers. It wraps all the complex code into a neat user-friendly interface. The second one is a raw code notebook that I made completely free and available for everyone. I want to be clear right up front, both of these notebooks do the exact same thing at the end of the day. The core extraction engine is identical. The web UI version just saves you a few extra clicks and some manual file routing. In this video, I'm going to walk you through both methods. After we create our custom LoRA, I'm going to head over to my GitHub repository to grab a recent notebook that I built specifically for Z-Image Turbo generation with custom LoRA support, and we will take our newly minted LoRA over to Google Colab to actually test it out and generate some images. Now let's open up our browser and get into it. First things first, navigate over to kaggle.com and make sure you are signed into your account. Once you are on your main dashboard, you want to look over to the left-hand navigation menu. Click on the Create button, and from the drop-down, select Notebook. This gives us a completely blank slate to work with. Now, instead of writing complex Python code from scratch, we are going to import the custom notebooks I built. Move your mouse up to the top left corner. Click on the File menu and select Import Notebook. A drag-and-drop window will appear on your screen. For the first part of this showcase, I am going to demonstrate the exclusive Web UI method. I browse my local files and select the file named Z-Image LoRA Web UI IPNB. Once you click Import, Kaggle will load the notebook directly into your workspace. Before we even think about touching the code, we absolutely must assign the correct hardware to this session. This is a crucial step. If you skip this, the entire process will fail because the default CPU won't cut it. Look over to the right-hand sidebar. Scroll down until you see the Session Options panel. By default, the accelerator might be set to None. Click that drop-down menu and select the GPU T4x2 option. Kaggle will prompt you with a pop-up warning you about your weekly GPU quota usage. Just go ahead and click Turn on GPU T4x2. You will notice the session status in the top right corner will spin and say starting for a few seconds as Kaggle provisions a dedicated virtual machine with those dual GPUs and 30 gigs of RAM just for us. Alright, our hardware environment is ready to go. If you look at the main window of the notebook, you will see it is incredibly streamlined. It consists of just a single cell of Python code. This script is designed to be a true one-click solution. It handles absolutely everything. It installs Gradio to build our user interface. It pulls in the model scope and safe tensors libraries, and most importantly, it clones the DiffSynth Studio repository directly from GitHub. This repository contains the core architectural code we need to run the Z-Image pipeline. I am going to hit the play button on the left side of the cell to execute it. Now, we just have to be patient. If you look at the console output expanding right below the cell, you can see the background process is happening in real time. It is updating the Linux package lists, installing ARIA 2C, which is a high-speed parallel download utility that will pull our massive model weights much faster than a standard Python download script, and it is fully configuring the DiffSynth environment. This initialization process takes a minute or two. As the installation finishes up, you will see a message in the log saying environment successfully configured, followed by starting UI server. Finally, Gradio will generate a public web link at the very bottom of the output. It will end in Gradio Live. I'm going to click that link, and it will open our custom user interface in a brand new browser tab. Welcome to the Z-Image Instant LoRA Extractor Web UI. As you can see, I designed the interface to be broken down into very easy, logical steps. On the left side, we have our input configurations, and on the right side, we have a live terminal log. This log is super helpful because it allows us to monitor exactly what the backend Python code is doing without having to switch back and forth to the Kaggle tab. Step 1 is uploading your dataset. Remember, the beauty of this method is that we do not need hundreds of images. Just 1 to 6 images are more than enough to capture an aesthetic. I'm going to click the upload box and navigate to a folder on my computer where I have prepared a specific dataset. Now look closely at these reference images I'm selecting. I have intentionally chosen portraits of different people and even an animal that all share one very distinct, extreme visual characteristic: wild, frizzy, chaotic, static shocked hair. My goal here is to create a LoRA that forces this very specific, messy hair texture onto absolutely any subject I prompt later, regardless of whether it's a person, an animal, or a character. I select all 6 images and click Open. The Gradio interface quickly uploads them to the server. Step 2 is naming our LoRA. By default, the text box says My Custom Style, but I want to keep my files organized so I know exactly what this file does later. I'm going to click into that text box, delete the default text, and rename this to Hair LoRA. With the reference images loaded and our custom name set, I'm going to click the big blue button that says Generate LoRA. Immediately draw your attention to the live terminal logs on the right side of the screen. Because this is our first time running the extractor in this current Kaggle session, the system needs to download the foundational AI models. Using that ARIA 2C high-speed downloader we installed earlier, it is rapidly pulling down tens of gigabytes of necessary data. You will see it downloading the Dynov3 Vision Transformer, the SIGLIP image encoders, the Z-Image specific model weights, and the massive Tongi text encoders. These models are absolutely essential for the extraction to work. The vision encoders are going to look at our 6 uploaded images and translate those raw pixels into deep mathematical representations of what chaotic hair actually looks like to an AI. The text encoders then ensure that this visual data is perfectly aligned with how the AI understands natural language prompts. While it runs, let's talk a bit more about what the Z-Image pipeline actually is. Developed by Tongyi Mei, the Z-Image model developer. This is a zero-shot extraction pipeline. Instead of training a model over thousands of steps to slowly learn a concept, it takes your reference images, passes them through incredibly powerful vision encoders like Dynov3 and SIGLIP, and dynamically generates the exact mathematical weights needed to replicate that style in a low-rank adaptation format. It bypasses the traditional gradient descent training loop entirely. Once the downloads hit 100%, the script moves on to the next phase. It loads these massive pipelines directly into the VRAM of our T4 GPU. It uses a highly optimized bfloat16 data type to save memory. Then comes the actual extraction process. You will see the terminal update with the message: extracting stylistic DNA, GPU is crunching the math. This is where the heavy computational lifting happens. When I ran this through the web UI, it took exactly around 5 minutes for the script to completely process the images, extract the latent representations, and synthesize the final LoRA weights. Once it finishes, the terminal will display a success message stating that Hair LoRA Safe Tensors is ready for download. Right below the terminal log in the final output section, a downloadable file block has automatically appeared. I simply click the download icon, and just like that, we have a fully functional, custom-made 113 megabyte Safe Tensors LoRA file sitting locally on our hard drive. Altogether, it took me 10 minutes from running the Kaggle notebook cell to generating my first LoRA, so 10 minutes is an incredibly fast turnaround compared to traditional Dreambooth training, which can take hours. Now, let's use the raw notebook version that achieves the exact same result. It just requires a bit more manual navigation. Let's switch gears and look at that second method. I'm going to close out of this Gradio browser tab and head back to my Kaggle workspace. To keep things clean and prevent any memory conflicts, I'm going to stop this session and load up my notebook file into my Kaggle interface. I'll click Import Notebook. This time, I'm selecting the file named Z-Image LoRA raw IPinB. You should confirm from your session options that you're using the T4 GPU before proceeding. Scroll down to the cell labeled Step 1, Environment and Engine Setup, and hit the play button to run it. This performs the exact same initial setup sequence as the web UI. While that initialization script runs, we have to handle our dataset differently. Since we do not have a convenient Gradio drag-and-drop box here, we need to feed the reference images directly into Kaggle's internal backend storage. Move your mouse to the top right of the screen, just above the sidebar, and click the plus Add Input button. A menu pops up, and you need to select Upload a Datasets. A new dialog window appears. I click the Browse Files button, navigate back to my local desktop folder, and select those exact same 6 reference images. Now, pay close attention to this next part. Kaggle requires us to give this uploaded dataset a title, and that title must be globally unique across their entire public platform. If the dataset is private, you'll have to make sure you have no such file name existing. Watch my screen as I try this. I type in the word images into the title box. Kaggle instantly throws a red error saying, the requested title is already in use by a dataset. So, I try modifying it slightly and type images with 2 S's, still giving same error due to cache. So, I'll have to click on the earlier images dataset to delete it. Finally, I type in the word samples. The error disappears and I get the green check mark. Perfect. I click the Create button in the bottom right corner. Once the progress bar finishes and it says Success, I close that pop-up window. If you look closely at the input section on the right sidebar now, you will see a new data source folder called Samples. I click on it to expand the directory, and there is a list containing all 6 of our uploaded images. To use these images in our code, hover your mouse over the folder name Samples. A tiny icon that looks like 2 overlapping squares will appear. This is the Copy File Path button. Click it to copy the internal Kaggle directory path directly to your clipboard. Now, scroll down the notebook to the cell labeled Step 3, Generate Z-Image LoRA instantly. Look at the Python code block. At the very top, we have a defined variable called Dataset Path. I am going to highlight the placeholder text inside the quotation marks and paste the directory path I just copied from the sidebar. Right below that is another variable called LoRA name. I am going to click inside those quotation marks and name this output LoRA Safe Tensors. With those 2 variables set, I click the play button to execute cell 3. Just like the web UI process, this script now takes over completely. Because this is a brand new Kaggle session, you will see the output log utilizing ARIA2C to pull down all the Dino, VAE, and text encoder models once again. After the downloads, the script normalizes our uploaded images, extracts the stylistic features into latents, and synthesizes the LoRA weights. For the raw notebook method, this entire process took me around 13 minutes to complete. It is slightly longer than the 10 minutes it took on the web UI, mostly due to the extra time we took in creating the dataset and deleting the existing one, and it'll get you the exact same result. Once you see the final console output print, Success, Saved Kaggle Working Output, we need to retrieve our generated LoRA file. Go back to the right sidebar, scroll down past the input section and look at the output section. Click to expand the Kaggle Working folder. Inside that, you will find an output folder. Expand that, and right there is our compiled LoRA Safe Tensors file. Click the 3 vertical dots next to the file name and select Download to save it to your computer. Okay, training the LoRA is done. Now, we need to actually prove that it works by generating some images. While Kaggle was necessary for the heavy 30 GB RAM extraction phase, you can achieve this on Google Colab if you have some pro credits to spend with this same notebook. Now, I'm going to head over to my GitHub repository. I open a new browser tab. I open up my Colab Notebooks repository, and scrolling down the list, I find the notebook I just recently made titled Z-Image with LoRA support. I right-click the blue Open in Colab badge and select Open Link in New tab. Welcome back to Google Colab. Before we can start generating images with our LoRA, we have to solve a minor logistical problem. Colab provides a temporary workspace. Every single time you start a session, the virtual hard drive is wiped clean. If we manually upload our 113 megabyte LoRA through the Colab interface every time, it will take forever. To solve this efficiently, we are going to use Google Drive as our permanent high-speed storage. I open a new tab and navigate to my Google Drive account. I simply drag and drop the Hair LoRA Safe Tensors file we just downloaded from Kaggle straight into my drive. Once it is sitting in Drive, right-click the file, scroll down to Share, and click Share again. By default, Google Drive files are set to restricted access. We need to change this so Colab can read it via an API. Click the drop-down menu under General Access and change it to anyone with the link. Click Copy Link. Let's head back over to our Google Colab tab. Scroll down to Step 2, High-Speed Asset Downloader. You will see a dedicated text box labeled LoRA URLs. I'm going to paste the Google Drive link I just copied right into that box, but our LoRA cannot generate images on its own. It acts as a style filter applied over a base model. I recommend you use a GGUF version of the Z-Image model if you're trying it, also on the free T4 GPU, due to memory constraints, but you can also give the FP8 version a try as well. To get this model, I open a new tab and go to huggingface.co. In the search bar at the top, I type in Z-Image Turbo. I'm looking for a GGOF version of the model, and here's one provided by Unsloth. I click on the Unsloth Z-Image Turbo GGOF repository. I navigate to the Files and Versions tab. Here you will see a list of different quantizations. For this workflow, I'll go for the larger one, which is the file labeled Q8.GGOF. This 8-bit quantization offers the absolute perfect balance between a small file size and incredible output quality. But feel free to try all the other ones as well. I'll right-click the download arrow icon next to the file size and select Copy Link Address. Let's jump back to our Colab notebook and then paste this Hugging Face link into the text box labeled UNet URLs. Now, our assets are mapped. Once Step 1 finishes, I'll run Step 2. You will see the console fetch our GGUF base model from Hugging Face and pull our custom Hair LoRA straight from our Google Drive. With all files downloaded, scroll down to Step 3, Image Generation. First, we need to map our files to the prompter. In the UNet FREEious box, you must type the exact file name of the main model. I'll type in Z-Image Turbo Q8 GGUFS. Next, in the LoRA FREEious box, I'm typing the exact name of our custom file, Hair LoRA Safe Tensors. Now for the prompt, let's keep it simple for our first test. In the prompt box, I type lady in a car. For the negative prompt, I will add standard limiters like blurry, low quality, deformed artifacts. Finally, take a look at the LoRA strength slider. A value of 1.0 means the script will apply our custom style at 100% intensity. You can increase or reduce it depending on the level of LoRA effect or influence you'd want to apply for your generations. Now let's hit the play button on the cell. And after a short while, an image renders directly below the UI. Look at that result. It generated a realistic image of a woman sitting in a car, but her hair is absolutely insane. Although not as insane as our training images, but it greatly mimics the chaotic, frizzy style from our Kaggle dataset, and you can increase or decrease the LoRA influence from the LoRA strength slider if need be. As you can see, the LoRA didn't break the car or her face, it surgically targeted the hair texture. Let's try another generation. Let's scroll back up and change the prompt to a cat and a dog. Let's see if the weights understand the concept well enough to apply it to an animal, especially that our dataset contains animals as well. The result loads, and it is interesting. We have a photorealistic cat and dog, and both are rocking some sort of electrified bedhead fur. It transposed the style perfectly. Let's try one more. I changed the prompt to lady and a guy. I hit generate. The result is fantastic. Both the man and the woman feature the exact same frizzy hair aesthetic blended into a cinematic portrait. These results aren't as impressive, so it'll boil down to how well you're able to play with parameters and the quality of your image datasets and its consistency during your LoRA training. And also, keep in mind, if the effect is ever too strong, you can just lower the LoRA strength slider to 0.5 to blend it more subtly. Once you're done generating, scroll down to the very last cell labeled Step 4, Export and Download Results. Run this cell, and it will instantly compress all the full-resolution images you generated into a zip file and download them directly to your computer. And that is it. All links will be dropped in the description below, and before you leave, make sure you go to the top right of Colab, click the RAM dropdown, and select Disconnect and Delete Runtime. Also do the same on Kaggle when you're done extracting LoRA. Don't forget to like, subscribe, and let me know in the comments what crazy styles you extract. Have a great day, and I'll see you in the next one.